All right, so we're going to start by looking at radicals. Okay, we'll do a few things. We're going to solve radical equations. We're going to do graphing, describe transformations. It's pretty much, we're going to do everything with radicals today. It's just kind of its own one section, and then we're done with radicals. Right, so just one day on. So radicals are equations that have different kinds of roots in them. They can be square roots, they can be cube roots, but they have to have some kind of root. So I want to go through some different terms because there's names for the thing underneath this number right there. I just want to make sure we know what those are called. So first of all, that number that's outside the root, okay, that is called the index. And the index tells you what kind of root you're working with. If you don't write an index, like in the first one, it's assumed that you're working with an index of 2, which means square root. If you want to do any kind of root other than a square root, you've got to put the index. The index has to be a positive number that's an integer, and it has to be bigger than 1. So you can't have an index of like 3.5. You can do a cube root, you can do a fourth root. There's no root we're going to talk about in between the two. The symbol, this entire thing, this expression, that is called a radical, or a radical expression. So like this part in green right here, or blue I guess, that's a radical expression. If you include the y equals with it, that's a radical equation. The part that's underneath the radical, okay, that's called the radicand. And then the actual symbol itself, that's just called the radical sign. So any questions on the terms radical, radical expression, radical equation, index, or radicand? Okay. I told you that a minute ago. If there is no index, we always assume it's 2. And when we write a radical, you can do it on the calculator, like if you wanted to do square root of a number. We have a button for square roots. Second, x squared, and that's how you type in a square root. We'll talk about how you can do other roots in a little bit. Now, instead of writing the square root of 52, there's a power I could raise 52 to and get the same answer. What can you use as an exponent? And it gives you the same result as taking a square root. Yep. 1/2. Raising something to the 1/2 power is exactly the same as taking the square root. How about if I wanted to do a cube root? What power would I raise to there if I don't want to write the cube root symbol? Yeah. 1/3. I can raise to a 1/3. Yep. And how about a fifth root? I can raise to the 1/5. And this last one, we might want to do something like that because then you have your radicand to the 1/5. Well, the radicand had a power in it. This is a power to a power. What's x to the 4th to the 1/5? Yep.
Isn't that just x to the 4/5?
X to the 4/5. Yep. So that might be a reason why you would write something as a power rather than a root, because there's something you can simplify it with on the inside. Now, this you can't simplify anymore. When you have a binomial or a polynomial raised to a power, you do not raise each term inside to the power. That's not how it works. This one I could simplify because it was a monomial raised to a power. That's different. Any questions on that idea? So let's take a look at, if I ask you to solve for what's called the principal root. So first of all, solving for the principal root means that you are finding a single answer. A single answer. And then we're going to break that up into two cases, whether we're dealing with an odd root or an even root. So if I asked you to find the cube root of 64, and somebody said, I don't know what that means. Okay? I don't understand what that means to find a cube root. So the way I would explain it is you're basically trying to find a number that you can raise to the index, or in this case, to the third power. And when you find that number that you raise to the third power, it needs to come out to your radicand, 64. That's how I would explain what a cube root is. Something to the third power gives you 64. In this case, x is how much? Yeah, 4. Yeah, x is 4. So that's what it means to find the principal root of the principal cube root of 64. The answer is 4. Now, you could also do that. Cube root of -8, no problem at all. What times itself 3 times gives you -8? Yeah? -2. So finding principal roots of odd roots, you can do negative numbers, you can do positive numbers, you can do 0. Cube root of 0 is 0. The domain for odd roots is always going to be all real numbers. Now, even roots, it's a little different. When you're dealing with an even root, and I say find the principal root, the first condition is that the radicand is 0 or higher. Why do we want the radicand to be 0 or higher when you're doing an even root? Yeah?
Because you can't square a negative.
You can't square a negative?
Well, I know you can't square a negative, but it's the same, like the fourth root.
I know what you mean.
Because you get I.
But you can square a negative number. But I know what you're trying to say. Yeah?
It'll become imaginary.
Because what are you trying to do? You're trying to...
Square a negative.
No, you can square a negative. That's fine. But you can't do what? Yeah.
Square a root.
You can't square root a negative. All right? But I know what you mean. So when you're trying to take a square root, if this is an even index, you have to make sure that this is 0 or higher. Otherwise, when you take the root, it will come out imaginary. Okay? So that still leaves you with 2 answers. We always want the one that's not negative if the directions say principal root. So if I add the square root of 36, somebody asked me to explain, what does that mean? I would say that there's a number you can raise to your index. And when you raise that to your index, you will get your radicand. That's what it means. So in this case, some number to the second power gives me 36. Well, there's 2 numbers. 6 times 6 is 36. -6 times -6 is 36. So if the question just said, find the roots of 36, that's different. There's 2 answers. But if it said, find the principal root of 36, I would want the answer that is not negative. Notice I didn't say positive, because you might do the square root of 0. And if I said, give me the positive answer when you do the square root of 0, well, there isn't one. The square root of 0 is just 0. Right? So you're looking for the answer that is not negative. So, any question on the difference between the two? Odd root versus even root. Still the same concept. You're still trying to solve an equation that looks like this. Right, it's just with odd roots, negative answers are okay. With even roots, they're not. For principal roots. All right, so now let's look at what happens here. So we've got a number, and we're going to take the square root of it. And we're going to look, when we take the square root, if it gets smaller or larger. See what I did there with the font too? Smaller and larger. All right. So we've got 4, and I want to know what's the square root of 4? 2. So did that get smaller or larger?
Smaller.
All right, it got smaller. So maybe when we take square roots, they always get smaller. Let's try 18. Square root of 18 is about 4.24. Okay, still follows the pattern. It got smaller. Can anybody give me an example where when you take the square root, it doesn't get smaller? Yep.
A quarter.
A quarter? What would happen there?
It would be, it would go to a half.
Yeah, when you take the square root of 1/4, you get 1/2, so it actually gets bigger. But I was even thinking of something else, kind of in between the two. Anybody think of a square root that doesn't get smaller or bigger? Yep. 1 or 0. Yep, they stay the same. So the answer to whether a square root is smaller or larger than the original problem, it depends. If your original number you took the square root of is greater than 1, it will get smaller. If it was exactly 1, it will stay the same. If it was 0, it would also stay the same. If it's between 0 and 1, like the square root of a half, it gets bigger. Okay, that's 0.71. So sometimes square roots get larger, sometimes smaller, sometimes they stay the same. So now we're going to take a look at what square roots look like. So we're going to graph 3 different, sorry, not just square roots, but even roots. We'll do a square root, a 4th root, and a 6th root. All right, so square root, you guys should already know how to type that. Second square root x. 4th root. The way you type in that, you do your index first, 4. You press math, and then you go to the 5th option down, which is xth root. Whatever number you typed in before, it's going to fill it in for the x. That's how you do 4th root. Okay. 6th root, 6, math, 5. There's your 6th root. And we could do 8th root. We don't really need to. I think you'll start to see the pattern with 3 even roots. We'll start with zoom 6, but we are going to adjust it. So there's your square root. That's your 4th root. And in black, you're seeing your 6th root. What patterns does anybody notice there? Anything at all? Yeah? Yeah. Okay. Yes.
It's just a curved line coming from the origin.
Yeah, they all come from the origin, right? So every one of the lines goes through the point 0, 0. Well, they're curves, they're not lines. Anybody notice anything else about where they're located? Yeah?
They're only in the first quadrant.
They're only in the first quadrant. And they do go through the origin, so they technically are on the axis at that one point. So let's zoom in closer so we can see maybe what's happening just in that section in quadrant 1. So let's do a y max of like 4. And I think everything else looks good. So square root, 4th root, 6th root. Okay, that should give you a little better idea of what's happening. Anybody notice anything else now about those graphs? So what did we say? They all go through 0, 0. Do they go through anything else? Which one? Where?
There seems to be like a point where they all intersect.
Yeah, where is that? 1, 1, right? If you take the square root of 1, 4th root of 1, 6th root of 1, you get 1 for all of those. So they all go through 0, 0. They all go through 1, 1. They're all in quadrant 1, which means that the domain and range are not negative infinity to infinity. We're going to write down what they are in a second. And how about which one is on top of them? Like if you think about like the graph that's above all the others. Is the blue one always above everything? Always below everything? Or does it depend? It depends. There's different behavior between 0 and 1 than there is after 1. Okay, when you get after 1, the square root is always on top of the 4th root, which is on top of the 6th root. So the higher the index, the lower the graph is after the number 1. If you look before the number 1, what I just said is reversed. The higher the index, the higher the root. The 6th root is the highest, the 4th root is the middle, and the square root is the lowest. So those are all important things to note about even roots. They all go through the point 0, 0, and 1, 1. Now, that's assuming you don't shift them. Okay, you can take a square root function and you can shift it up or down, just like anything else. If you shift it, then no, it won't go through the point 0, 0, and 1, 1 necessarily. Or if you stretch it. We saw that it was always in quadrant 1, except for the origin. That's not in quadrant 1, but it does start at the origin. But it always went to the right, and it always went up. That makes the domain everything from 0 to infinity, and the same with the range. And to describe which graph is above the other, you really have to describe it in 2 pieces. Are you looking between 0 and 1, or are you looking past 1? And that's the behavior we just described. And you can continue to extend that pattern 8th root, 10th root, 12th root. You can keep going. Okay, but that's just some basic facts about even roots. Okay, any questions about even roots? So now we're going to start to think a little bit about odd roots. When you're dealing with an odd root, what kind of numbers are you allowed to use in the radicand? If I said take the cube root of, and then what kind of numbers could I give you? Yeah? Positives or negatives, anything else? That's a lot of numbers, but that's not all of them. Yeah?
0.
Or 0, yeah. When you're dealing with odd roots, the radicand can be any real number. Any real number. Right? So if the radicand is any real number, that's your domain. If your domain is going to be all real numbers, what's that going to look like when you draw it? It's going to be a little different than an even root. Yeah?
It's continuous.
Okay, so even roots were still continuous, right? I never had to lift my pencil when I sketched those.
I meant like it's. I don't know how to explain it. It's going to go on behind the graph too. It's going to be in the negatives too.
Right.
It's not going to only be in the first quadrant.
Right, when we talk about a domain that's all real numbers, we're going to go left and right. Okay, so the graph is going to continue in both directions. Okay, so let's see what that looks like. And remember, it is always continuous. There's no number you can plug in, no real number, that you could take the cube root of and like get an error. That never happens. So let's just modify that to be a cube root and a fifth root. Start with zoom 6 so we get kind of a big picture. There's your cube root. There's your fifth root. So we notice it goes in both directions forever. But let's zoom in so we can see a little bit better. Let's set our x's are fine, but let's do -3 to 3 on the y's. What does it look like kind of happened when it sketched that? Yeah?
Broke apart.
Looks like it broke. It shouldn't do that, right? It's because the calculator can't do a good job graphing this kind of thing. It is continuous, but it doesn't look it because the calculator is just having trouble. Right. Let's look at this a little bit bigger. And does anybody notice anything about these graphs? I want to kind of go through the same things we just did for even. Yeah.
So, you know, like intersect that 1, 1, and -1.
1, 1, they intersect.
And then -1,
-1, -1, and where else?
0, 0.
Yeah, they do intersect at 0, 0. Calculator's just having a bad day. So they intersect at 0, 0. Think about the cube root of 0 and then the fifth root of 0. They are 0. How about which graph is on top? Is the red one on top all the time? The black one on top? Or does it depend? Yeah,
It depends.
it depends. And there's lots of intervals here you have to look at. Let's put in some vertical lines. Let's put one here, and let me do one more, but make it a different color so we can see it. Green. So this graph is really separated into 1, 2, 3, 4 sections. The red one is on top when you are in sections 2 and 4. The black one is on top when you're in sections 1 and 3. So it's a little more complicated to describe because there's more going on, but the graphs do change places a couple times. But that's what odd roots always look like. I refer to this as the center point. Okay? Anytime we graph an odd root, we have to find the center and then draw it in each direction. Anytime we find an even root, we have to find the start point and then draw in one direction. Okay, so that's the big difference between even and odd roots. All right, so let's summarize some of that. So those 3 points are common to all odd roots if you don't do any transformations. Okay, if you shift something up and down or stretch it left and right, well then yeah, those points all change. But I'm talking about no shifting, no stretching. What's the domain and range for these odd roots in every odd root? Yeah.
-infinity to infinity.
Yeah, domain is all real numbers. Odd roots go left and right forever. They go up and down forever. And then to describe which graph is above the other, I have to describe sections 1 and 3 together. And I have to describe sections 2 and 4 together. And that's what I've done right there. So if you're in sections 1 or 3, the higher the index, the higher it will be on the picture. If you're in the other 2 sections, the higher the index, the lower it'll be on the picture. Any questions on the characteristics of even or odd roots? All right. From now, we're going to look at transformations. Everybody have that? Okay. So transformations work exactly the same as every graph we've studied all year. So I've given you kind of the template that I always do with the A, B, C, D. And we'll go through them. I'm not going to write it all down because we've done it several times. So if you want to write it, you can. But let's start with A. What kind of transformation would A be? Yeah.
Horizontal shape.
Yep, A is your horizontal shift. It's adding inside the function. Positive would shift it to the
Lucas.
left and negative to the right. Okay, how about B? Still inside the function, but now it's multiplying instead of adding or subtracting.
Horizontal stretch.
Horizontal stretch, and B is backwards. The bigger you make B, the more compressed it gets. So if B was a 5, you would say horizontal, well, if it's 5, it's going to compress 5 times as much. So you could say stretch by 1/5, which means compress. Or if B was 5, you could say horizontally compress by a factor of 5. You could say it either way. If B was 1/3, you could say horizontal stretch by 3. Yeah, that'd probably be the simplest way to say it. If B is 1/3, stretches 3 times as much. How about C? What's that going to do? Yeah.
A vertical stretch.
Vertical stretch. If C is, say, 7, it's a vertical stretch by 7. If C is a half, it's a vertical stretch by a half. It actually compresses. So C is not backwards. And what about D? Yep.
Vertical shift.
Vertical shift. Positive is up, negative is down. What happens if B is negative? What would that do?
It would flip it like a reflection.
A reflection over,
The x-axis.
if B is negative, that's a horizontal reflection, which means it would go from this to that. So that would be over the y-axis. What about if C is negative? What would happen there? Yep.
Reflection over the x-axis.
That's a reflection over the x-axis, or you could also say vertical reflection. It would look like that. Right? So there's 6 different things that can happen. 2 shifts, 2 stretches, 2 reflections. The parent function that you're always using to compare to, like if you're doing square roots, is that. If you're doing cube roots, that's the parent function. It's the simplest version of the root you can have without any stretch, shifts, or reflections. All right, so let's look at g of x. We've got the square root of x minus 2, and we're comparing that to the square root of x. You'll never compare like a square root to a cube root. You won't ever do that. What would be the transformation to turn the square root of x into the square root of x minus 2? Yeah.
You start at 2, 0, 2, 0.
So how would you, like if you're going to write like a sentence that describes the transformation?
Shift to right 2 units.
Yes. Shift, and the assumption here is the parent function. Shift the parent function. Right. 2 units. Yep. How about this one? How would we get h of x? Starting with the parent function. Yep.
Shift to the left 3 units.
Okay, so shift the parent function left 3 units. And this last one, we've got to kind of fix first. What's wrong with that? Yeah.
You put the X term first.
Right, it's not set up to match the template with the ABCD that I gave you. How would you rewrite that so it matches it?
Negative X plus 3. All under the root.
Yep. Negative x plus 3. So how many transformations are happening in this one? 2. And you do have to describe them in a certain order. And the order is A, B, C, and D. Do them in that order. So what would we say first?
We would say shift left 3 units.
So shift left 3. And second and last. Yep.
Reflect over the y-axis.
Yep, you could say horizontal reflection or reflect over the y-axis. Probably more specific to say reflect over y-axis, because if you say horizontal reflection, you're not really saying what to reflect over. There's lots of horizontal reflections. But yeah, reflect over y-axis is probably better. Questions on that? All right, so sketching. When we are sketching a radical function, you have to find, for your first point, you have to find the new center or start point. If it's an odd root, it's a center. If it's an even root, it's a start point. So regardless, it was the point that was at the origin in your original picture. To figure out where that point goes, we can start by finding where the x value goes by setting the radicand equal to 0 and solving. So if we go back to that template, the only two values that are going to affect the left and right movement of the point that was originally at the origin are A and B. You can do whatever you want with the C and the D, and it has no effect on this. The C and the D could affect if it goes up and down, not left and right. So once you get your x value, you'll have a formula kind of like this. You're going to get your x value first by doing what I said right there. Take that number and plug it back in, simplify, and then you'll get your y value. So you're going to substitute your x value back in, simplify, and then you'll get your y value. So that point's good. It gives you either where the graph is going to start or the center, but you still need some more points. If it's the start point, I would suggest maybe 2 or 3 more points to get an idea of the curve. If it's a center, you're probably going to need a couple points that way, and maybe a few points the other way. So odd roots are a little bit more work to sketch because you got to go both directions to sketch. Even you only have to do one. Right. So let's try this graph. Okay. When I sketch that, is that graph going to have a start point or a center point? Yeah. Right, it's going to be a center because the index is odd. So that means I need to check points on both sides of the center once I find it to make my sketch. Okay. What's the equation we would write down to find the new x value of the center point? We have to write it down, then we have to solve it.
to set the Radicam loop to 0.
Yes. And what? How can you tell me what that would look like?
The cube root of 3 minus 2x equals 0.
So what you said to do was right, but you didn't do what you said. But you did say the right thing to do. We just have to do exactly what you said. Yeah?
You can just make a new equation that says 3 minus 2x equals 0.
Yes, 3 minus 2x equals 0. The radicand isn't the root, it's what's under the root. So solve that. And you're going to get 1.5. Okay, that's the new x value of what was the point that was the center at the origin. Okay, now to find the y, we're going to plug that back in. Fill that in. What's 2 times 3 halves?
It would be -3.
Negative 3. What's 3 minus 3?
0.
0. And the cube root of 0?
0.
0. Times 2?
0.
Still 0. Plus 1? 1. So basically that number at the end is what controls where the point moves up and down. All right, so we've got our center. Now, to get some other points, the fastest way is to use the calculator. You don't need the graphing calculator. Excuse me. Thank you. But it is faster if you use the table to plug it in. Then you don't have to try to pick numbers by hand and do it out every time. But you could. It's not impossible. So we need 2 times the cube root of 3 minus 2x plus 1. That's how it should look when you type it in. If we want to double check the center, we can. Just go to our table. Yeah, 1.51. That looks good. And then I'm going to pick 3 points to the right and 3 to the left. Let's do like 3, 5, 10. Let's do 0. That's a good one. Actually, 0, -5, -10. That's fine. So we're going to graph all those points. So I need graph. Okay. And let's see what we got. So we got the center at 1/2, 1, or 1.5, 1. We've got 3, -1.8. 5, we're at almost -3. And 10, we're at a little bit past -4. Actually, I gotta go down. Okay, so that's how it's going to curve to the right. And now let's go to the left. 0, 3.8. -5, -5.7. There. And -10, a little above 6.5. About there. Okay, that's pretty good. So, draw your sketch. That's what it looks like. Okay, let's check our graph and see how we did. Let me do zoom 6. It's going to get, it's probably a little steeper in the middle than I drew it. That's okay. But because it got pretty steep, the calculator broke it into 2 pieces. Remember, that is not, there's no hole in the graph or anything. These graphs are continuous, every one that we've done today. Okay. Any question on drawing an odd root? Now let's do an even. I'm not going to do the whole thing, but let's just look at first starting point. First of all, why does this have a starting point and not a center? Because it's an even index. Now, when you graph an even root, it normally curves which way? Yeah.
To the right.
It normally curves to the right. Are there any reflections in this one? What do you think? Any reflections? Yeah, please.
There be a horizontal.
I'm sorry, Andre. Yeah, horizontal reflection. What's that going to do? When you do a horizontal reflection?
It reflects it over the x-axis or y-axis.
The y-axis. So what normally curved to the right is now, it's going to curve the other way. It's going to curve to the left. So that means when you are picking values to check for x, you need to pick values that are to the left of your start point. If you try picking values to the right, they're going to come out imaginary. Okay, you won't be able to graph them. So what's the equation we would set up to find the start point? Yeah.
4 minus 3x
4 minus 3x
equals 0.
equals 0. So we're going to get 4/3. And what's the y value going to be? 4/3, comma. Yeah, -2. So when you are picking more x values to try, don't pick ones that are to the right of 4/3. I mean, try one, watch what happens. Pick 10. 10's to the right of 4/3. If you plug in 10, you're going to have 4 minus 30. It's -26. You can't take the 4th root of -26 and get a real answer. So you got to pick values that are smaller than 4/3. I would probably do like 0, maybe -3, -5, -10. That's plenty. So any question on how you'd sketch that even root? It's going to look something like this. All right. So last thing, radical equations. Depending on whether it's an equation or an inequality and the complexity, we can do it by hand or we can do it on the calculator. We'll do 2 by hand, and then if you have to do 1 on the calculator, if we don't get to something like that, let's say we had something like this. It's not hard on the calculator. You just put one side on y1, you put the other side on y2, and you'd be looking for where the square root is above the horizontal line at 1. So you just have to graph it and look at it. Calculate and intersect is usually part of it. But I want to focus on the harder part, which is doing it algebraically. When you want to solve a radical equation algebraically, you have to isolate the root. If you have an equation that has more than one root, isolate one of them. It doesn't matter which one, just isolate one of them. And then you need to cancel out your root by raising to a power. If you're dealing with a square root, you're going to square. If you have a cube root, you're going to cube. Probably not going to do a problem with a cube root where you would have to isolate it twice, because that would start to get pretty messy. We're going to do a square root that you have to isolate twice. That's the worst thing that happens in that problem is having to FOIL. That's as bad as it gets. Okay, but we're gonna do one that is a little simpler to start, and then I'm going to come back to the one that you have to do twice. You do want to check for extraneous solutions. It's not as simple as just saying, oh, will it cause me to divide by 0? Because there are no fractions in this. So you really got to plug your answer in and check it. So let's start with one that's a cube root, but you're not going to have to cube each side twice. It's only going to end up cubing each side once. Let's look at this one. So first question to ask yourself is, look at the root. Is the root isolated on one side? Yes. There's nothing outside that root on the same side. So we've got a cube root. What would cancel cube root? Yeah? Cubing. So we're going to cube each side. When you cube each side, you end up with x squared minus 2x plus 2 equals x cubed. And what do you think we would do next there?
Would you factor the left side?
We are going to try to do some factoring. So good idea with the factoring, but I want to rearrange this a little bit before we do that. Yep.
Would you put the x cubed on the other side so that so it's equal to 0?
Yeah, I want to get it equal to 0, but I'm going to put everything on the right, even though that's more to move, just because I always like the highest degree term to be a positive. But yeah, we want to get everything on one side. So let's do x cubed. Let's bring the x squared to the other side, the 2x, and the 2. Now, we do want to factor here. What kind of factoring are we going to try to do here? This is 4 terms. Yeah?
You're going to want to factor the x cubed and the x, negative x first.
Okay, so do you remember what kind of factoring that is when you factor what you can out of those 2 first? The x, oh, did I forgot to put that? X to the second. Thank you. That's important. Does anybody remember what kind of factoring this is? Yeah?
Is it group?
Yeah, by group factoring. So we're going to factor what we can out of these 2. What did you say to factor up?
X squared.
So x squared. Factor what you can out of the last 2. What factors out of 2x minus 2? The 2. Yeah, we can factor out the 2. And what would that leave you with?
X minus 1.
Yep, perfect. X minus 1. And now what does each term have in common there? Yeah. X minus 1. So factor that out. Now, what do you do with each factor? Yeah. Yeah. Set them equal to 0. What's going to happen if you set this equal to 0 and try to solve it? Okay.
Get the square root of -2.
You get the square root of -2, and what's going to happen there?
It's going to be imaginary.
It's going to be imaginary. So we don't have to even worry about that. That doesn't help us. Only part we got to worry about is this factor, which gives me an answer of 1. Okay, go back up and check it. 1 squared is 1, minus 2 times 1, plus 2, and plug 1 in on the other side. -2 plus 2 cancels. Cube root of 1 is 1. And I have 1 on that side. I get 1 equals 1. We solved it correctly. Okay, so that's an example where you just have to raise each side to a power once. Now we're going to finish with one that you have to raise each side to a power twice. But I told you if you have one that you have to do twice, it's not going to be any more than square roots, because that gets pretty bad if it's not. Okay, we've got two roots. We're going to have to raise to a power that cancels each root separately. So, first step, is the root isolated on one side? What do you think? Daniel, what do you think? No. How could I get, let's say, this root by itself?
You add the other one.
Yeah, let's add the other one to the right side. So we have that. Now, what could I raise each side to that would at least help me to start canceling out some of these roots? Yep.
2.
2. Raise each side, not each term. You cannot raise terms to a power in an equation. You have to raise the entire side. So on the left side, that's the easy part. That's now just 6x plus 12. The right side, we need to FOIL that out. So it's like you're multiplying 1 plus that square root times another copy of 1 plus that square root. And then you got to distribute it all out. So when you distribute, you'd get 1 times the square root, and another 1 times the square root. So you're going to get 2 copies of 1 times that square root. And then the last part is the square root of 4x plus 9 times the square root of 4x plus 9, which would give me how much? Yeah.
2x plus 3. Oh, I see.
So it's the square root of 4x plus 9 times another square root of 4x plus 9. Okay.
4x plus 9.
4x plus 9. Now, how many roots do we have left in that equation? Oh, Alex.
1.
Yeah, just 1. So now get that root by itself again, and then square each side. There's a lot of like terms we can put together first. So we can combine the 1 and the 9 and get 10. And then we can start moving stuff to the other side, but let's do that separate. Okay. How would I move the 10 over to the left? Yeah.
Subtract 10.
Subtract 10. How about the 4x? How would I move that over? Yeah. Subtract it. That's gone. So now you've got 2x plus 2 equals 2 square roots of 4x plus 9. So it's getting better. Is the square root by itself? No. And William, what do I have to do to get the square root alone?
Divide both sides by 2.
Yep. Divide everything by 2. Now, how am I going to get rid of that square root on the right side?
Square it.
Square it again. Square it. Square it. Just like before, the left side is double distributive. X squared plus 2x plus 1. Don't square the x and square the 1. That's not how you square a binomial. You've got to use double distributive property. So x squared plus 2x plus 1 equals 4x plus 9. And now we're down to what kind of equation?
I don't know what kind of equation we just said.
Yeah, we're gonna get it equal to 0, it's a quadratic. Right, so get it equal to 0. I would minus the 4x and minus the 9. And now finish that off however you want. Use quadratic formula, complete the square, or try to factor it. Okay, this one might factor. If you do 4 and a 2, x squared minus 4x plus 2x, yep, that's how it factors. So you get -2 and +4, but you need to check them. They might both work, they might both fail, or you might get one works, one doesn't. But I'm going to leave that part for you. Okay, so that's a complicated one. You have 2 roots, you got to do it twice. But I would expect more kind of like this. You only have to do it once. All right, so those are the questions for tonight. While you're at lunch, I'll pause it and I'll put the test topics in at the end of the week.